Okay, so guys, the topic for your notes today is writing chemical formulas for what we call the simple salts. Now, guys, the hope is that as you read those words, that last word brings back some rich memories from the last unit about this idea of salts. And we're going to start by reviewing what salts are. But guys, this is actually sort of the overview for this entire unit. So I told you this unit is mellow. I told you this unit is pretty darn accessible. I told you this unit is not conceptual. It's actually just stuff you've got to be able to do. So what are we going to do in this unit? Well, guys, in the last unit we talked about salts and molecules. We'll talk about how they're different in a minute. But guys, for this entire unit, you're going to learn one thing: how to write the names and formulas for salts and molecules. So guys, we've been throwing formulas at you, and on the test you identified whether they were salts or molecules. You figured out which atom was more electronegative, stuff like that. Guys, in this unit, 3 days, in this unit, you're going to learn how to name these things. And then for the rest of the year, when you go into lab, you're not going to have to walk up to the table and go, where's that ALNO33 stuff? You're going to be able to walk up here and go, where's the aluminum nitrate? And you're going to know the names and formulas for these salts and molecules. So here's the way we're going to handle this. Today we're going to do what we call the simple salts. On Friday, we're going to do what we call the complex salts. And then, guys, the next week, we're going to do molecules. So, what's the difference between salts and molecules? Do you remember? What's the difference between a salt and a molecule? What kind of bonds does a salt contain? Ionic bonds formed by cat, a metal and a nonmetal. So guys, remember, metals are big and fat and weak. Nonmetals are small and strong. When they get together, the nonmetal beats up on the metal, steals its electron. This becomes negative, that becomes positive. They attract, that's a salt. Sound familiar? Okay. And then guys, the nonmetals, those are the molecules. They're both small and strong. They pull on the electrons. They force to share. What kind of bonds are those? Covalent bonds, and that forms molecules. So guys, that's the way we're going to handle this. We're going to look at the simple salts, the ionically bonded guys, then the complex salts, still ionically bonded, and then molecules. So guys, in order to get into this, let's review. I pray you don't have to write this down. So here we go. Guys, metals, where are they on the periodic table, left or right? On the left, big or strong, big or small? Big, weak or strong? Weak. So what do they do with electrons? Give them away. Okay, so guys, here's what we know. Metals are large and weak, and they donate electrons and they form cations, right? Okay, where are the nonmetals? On the right, big or small? And check this out. This is good. Extra credit projects. Interestingly, none of you chose to do this. I have no idea if I can turn this on its side. But guys, do you remember the extra... There went Frankium. This is gross. This is homemade Play-Doh. Who knew? But this is really cool. So this is Drew Nielsen. This is pretty cool. So here's what he did. So the sizes of the balls are actually the sizes of the atoms, and then the colors of the balls represent their electronegativities. This is brilliant. I love this because you can literally see as you go down they get bigger, and as you go to the right they get smaller. This is good work. But guys, what we're seeing here is what we're reading there. As we move to the right, these things get smaller. I'm thinking about spraying this with lacquer down in Mr. Gurr's shop so it'll actually not dry out. He made his own Play-Doh. Is that cool or sad? I'm not quite sure. Yeah, I don't know. I wasn't sure. But guys, so when we look at the nonmetals, the idea is this. They're on the right, so they're small and strong. As a result, they take in electrons and they form anions. Remember all of that? Then the idea is the positive and the negatives form ionic bonds. Those are the salts. Good? Okay, so guys, what you're going to learn to do today is you are going to learn the system for writing the formulas for salts. Now guys, there are a couple things we need to talk about along the way, and you are going to get this in your notes, but our goal for today is this. I'm going to give you the name for a salt. You're going to write its chemical formula. Here's how this works. Ready? Write this down. So guys, first of all, you need to know what chemical formulas are. So let's define them. Put this in your notes. So if you're going to learn to write chemical formulas, you need to know what they are. So guys, a chemical formula is simply a phrase or a thing that is used to represent a chemical compound. Now understand, it doesn't have to be a salt. We also write formulas for molecules. But guys, the idea here is that it's just used to represent a compound. And guys, these things contain two types of information. They tell you what the compound is made of. That means composition. And then they tell you the ratio of elements in the compound. So when you look at the formula for a compound, you're going to know, one, what is it made of, and two, how much of each one of those things is it made of. So I'll give you some examples you won't need to write down, and then we're going to be one step closer to getting, and you guys won't have homework tonight. You'll get it all done. So that'll be good. Okay, so guys, for example, and we're actually, each one of these things that I'm about to show you, we are going to use in lab, actually some of these next week, but all of them after Christmas. So you walk into lab and you grab a bottle and it says this on it, Al2N3. You don't need to write it down. But guys, that is the chemical formula for a salt. So what do you know about the salt based on its formula? First of all, what's it made of? Aluminum and nitrogen. How much of each? 2 to 3. So every 2 aluminums, there's 3 nitrogens, and this is actually what is called aluminum nitride. We'll talk more about that later, but you get the idea. So guys, this is another one that we'll actually be looking at, and if you ever want to find this stuff, look in your toothpaste. Guys, they put this stuff in toothpaste, because what's this stuff right here? Fluorine, but we call it fluoride. And guys, it turns out that all of our toothpaste contain fluoride because that makes the enamel on our teeth strong, keeps us from getting cavities. So guys, this compound, which is in toothpaste, is made of what 2 elements? Fluorine and calcium, and it's in a 1-to-2 ratio. We'll explain why it's in a 1-to-2 ratio in just a minute. So guys, these are the kind of salts we're going to deal with today. They are called the simple salts because they are made of a metal, calcium, and a nonmetal, fluorine, or a metal, aluminum, and a nonmetal, nitride. These are what are called the simple salts. Yep. Oh, absolutely, yeah, and we'll show you. There's all possible ratios, and that's what we're going to learn today is how do you figure out the ratios. Yep, absolutely. So guys, what about then Friday? Well guys, Friday you're going to run into salts like this. This is what is called a complex salt. So do you see it? What makes this complex? So we've got a metal, but what do we have over on the right? It's a molecule. And guys, you may remember this was actually on the test. Oh gosh, sorry. This was actually on the test. Oh boy, go back here. Sorry, I didn't grab my pen. You may remember you actually drew the Lewis dot structure for this. It goes nitrogen, oxygen, 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 boom, 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 boom. Goes like that. So we're okay. Oh, here, octet rule. Okay, so guys, the complex salts are simply the salts that contain these molecules with a charge which you drew the Lewis dot structures for all throughout the last unit. That's why we had you do those, because we're going to use them in salts starting on Friday. Is there something wrong? My pen skipped. We're what? Oh, sure, you guys are all critical, but I've seen your tests. All right. I just because I haven't graded them doesn't mean I didn't look. Look at you guys being all, you got the wrong. That's good though, right? Because all right. Good night. You guys are a tough crowd. All right. So guys, the bottom line is this. This is what, oh, stop laughing at, This is why we're not doing really hard stuff this week, because this is what I knew I was going to be up against. I know. So guys, this is the stuff that we're going to be doing today. Then we're going to bring this stuff into the conversation on Wednesday. Okay, all right. So guys, with that said, we need to talk about some guiding principles that are going to get us closer to being able to write these formulas and figure out these ratios. So guys, some of this you already know, but it may be worth writing down. But these are the foundational ideas that are going to get you where you need to go. First of all, the octet rule. Remember this from last unit? What does the octet rule say? Atoms want 8 electrons. Now guys, here's the trick. We talked about the octet rule relative to covalent bonds in molecules. That told us how many electrons these atoms would share. But guys, the same octet rule applies to salts. It simply tells us how many electrons they gain and lose. So the octet rule tells us that atoms want 8 valence electrons. But because we're now talking about salts, they don't get those 8 electrons by sharing. They get those 8 electrons by stealing or losing. And when we talk about that, we now need to talk about what are called oxidation numbers. Write this down. This is the important stuff. Guys, we now need to talk about what are called oxidation numbers or oxidation states. So let me define it for you. Guys, an oxidation number is the charge that an atom takes on when it is ionically bonded. It simply tells you how many electrons an atom loses or gains. But guess what, guys? We've already talked about this. This was actually in your very first homework assignment from the last unit. We just didn't call it that. So you ready? Check this out. Follow my laser. So guys, looking over here at group number 1, the alkali metals. How many valence electrons do all of these have? 1. Now, this group 2 is here. So all of these have 1 valence electron. So are they metals or nonmetals? These are metals, so they are big and weak. And what do they do with electrons? Give them away. So guys, how many electrons will all of these give away? 1. And when you give away 1 electron, what does your charge become? +1. Now pick up your periodic tables and super squint and look right above the abbreviations of the elements. See that number there? What is it? It's a 1, right? The plus is understood. Negatives will be there. Pluses are understood. And what are the numbers above all those elements? Do you see them there? Little itty bitty tiny 1s. See them? It's between the abbreviation and the mass. Guys, those numbers, and if you want to look down here in the decoder key, it tells you that those numbers are the oxidation numbers. They tell you how many electrons these atoms will lose, and these all lose 1. So now guys, do this. Group number 2, how many valence electrons do they have? 2. They're still metals, so what do they want to do with them? Give them away. How many will they give away? 2. What does their charge become? +2. What little itty bitty numbers do you see above all of those elements? +2. Because I'm not hearing back from you, so I'm afraid some of you don't see what we're looking at. Are you guys all okay? See the little 2s? Okay, so +1, +2. Now guys, let's skip the D's. Let's go over here to group 3. How many valence electrons do they have? 3. They're still metals. What do they want to do? Give them away. What will their charge become? +3. And guys, if you look at boron, what's the number above boron? +3. If you look at aluminum, what is the number above aluminum? +3. If you look at gallium, what are the numbers above gallium? And do some of you have 1? Do all of you have 1? Just some of you, right? Now guys, go down to indium. What's the number above there? +3. Then go down to thallium. What do you have? And +3. Why? So guys, let's answer why right now just for this group. So guys, we all understand plus 3, right? They give away 3 electrons. But think about this. Where are those 3 electrons? In the highest S and P. How many are in the S? 2. How many are in the P? 1. So guys, some of these atoms don't just give away 3. Some of them will also choose to give away 1 from the P and keep the other 2. But now here's the problem. All of these have 2 valence electrons in the S and 1 valence electron in the P. Some of them do give away 1 or 3. Some of them only give away 3. And for some of you, you don't even have the same numbers for 1 and 3. But now guys, do this. Allow your eye to now scan through the D sublevel. Guys, how many valence electrons do all the elements in the D sublevel have? 2. Now look at their oxidation numbers. 7, 5, 4, 3, 1. It's all over the place. Guys, here's the deal. These atoms do not always behave as we think they should. We're not going to get into the complexities of this. Understand that what's going on can be explained by the simple conversation that we had about the group 3 elements. Sometimes they don't give away as many electrons as they can. And guys, it turns out sometimes they give away more electrons than they should because frankly, especially in here, they start giving away D electrons. We're not going to worry about it. So what are we going to do with this? Well, guys, join me in your notes. Here's what we now understand. Many of these elements have very complex sets of oxidation numbers. So the question then becomes this, right? Which oxidation numbers are we going to use? Well, guys, here's the answer. It varies for the metals and the nonmetals. For the metals, these are the positive ones, right? For the metals, this is obvious. If there's only one oxidation number, use it. Potassium can only be +1. Magnesium can only be +2. Silver can only be +1. Aluminum can only be +3. If it's only got one number, it's the only choice you've got. But guys, what if it's got more than one number? Which one are you going to choose? Here's the misconception. Let me grab a periodic table. So guys, take a look, for example, let's just do, oh, this is interesting. So guys, I think this is the most recent version of this. And even for like sodium and potassium, they actually put the plus sign even if it's a positive. My periodic table doesn't have that. On this periodic table, the plus signs are understood and the negatives are there. It looks like on this most recent version, they also put in the positives. That's interesting. Okay, but guys, the question on the table is this. What if there can be more than one number? Which one do you use? For example, look at copper, element number 29. How many different charges can copper have? 2. What are they? +1 or +2, right? Are we all in agreement on that, given our tables are a little different? So guys, what do you notice about one of those 2 charges? It's in bold. Do you see it? And now if you go down and read the double top secret decoder key, it says oxidation states, and it says in parentheses, bold is most stable. So what does that lead you to believe in terms of choosing which one to use? Use the one in bold, right? No. Guys, you will not do that. You will not choose the one that's in bold because just because it's most stable, it doesn't mean that that's the one to pick. So how do you know which one to pick? You will be told which one to pick. And how will you be told which one to pick? Roman numerals. Guys, if there is more than one charge, you will be told which one to pick by using a Roman numeral. Now, do you know Roman numerals? And guys, understand, you don't have to know this through like 50. We only need to know that to figure out which Super Bowl it is. So guys, what's the highest that we need to go with the Roman numerals? In theory, 7, right? Because you can't give away 8 because those are the noble gases. So really, we should only need to go through 7. So guys, just a second. If you don't know the Roman numerals, here they are. I's are 1s, V's are 5s. If the little number comes before the big number, you subtract. That's why 4 is IV. If the little number comes after the big number, you add. That's why 6 is VI. Do you guys remember that magic moment when you learned this in like 2nd grade? I was that kid that thought this was really cool because of the logic behind it. I hope some of you were as well. So guys, it goes I, double I, triple I, then IV, V, VI, and VII. That's 1 through 7. You're seeing something though. Dodge the bullet. Go ahead.
Could it go on 8?
Yeah.
But 2 of them on here have pluses.
Yeah, so, but where are those 2? Yeah, they're in here, right? Yeah, the reason that that happens is because they start giving away d electrons. Notice that none of the noble gases are 8. They don't give away 8 electrons. So the reason that we do have some that are plus 8 is because they're actually dishing out d electrons. But understand this. This is interesting. Anything above 2 would have to be d electrons, right? Because the transition metals only have 2 valence electrons. So if they're giving away 3, one of those has to be a d electron, and all the more so up to 8. Do any of them go above 8? There are actually really exotic situations where these can even like give away 9. They're not listed here though. So, okay, are we good, y'all? We okay with it? Okay. So guys, here then we need to talk about the nonmetals, the negative ions. So guys, this is the scoop. If you look at the nonmetals and look closely at their charges, what do you notice about their charges? Some are plus, some are minus. Guys, it turns out that the nonmetals can sometimes can be givers or takers. We are going to treat them as takers. So we are going to use the negative charges for the nonmetals. We are not going to worry about the examples where the metals can be positive. Or we're not going to worry about the examples where the nonmetals can be positive. We're going to treat them just as negative. But then, guys, look at oxygen. What do you have for the charge of oxygen? -2. Does anyone have -1? A couple of you do. Guys, let me just tell you. So, all right, let me answer that one first. Have you guys ever heard of peroxide? Hydrogen peroxide, you put it on cuts. Guys, when oxygen goes -1, we actually don't call it oxygen, we call it peroxide. So with oxygen, we are only going to use the -2 charge. So if you have -1, don't worry about it. But if you run into other examples where the nonmetals can have more than one negative charge, here's what we're going to do. If there's more than one negative charge, use the number predicted by the group. Write it down and then I'll explain it. So guys, what does that mean? Well, so for example, this. Oh, you're still writing. You guys good? Okay, so take a look at oxygen. Some of you on your periodic table, including me, don't just have a -2 charge for oxygen, you also have -1. So let's talk. How many valence electrons does oxygen have? 6, right? 2, 4, 6. So oxygen's got 6. How many then does it want? 2. It wants 8. It's got to get 2 to get to 8, right? So for oxygen, we're going to use the -2 charge because that's the one predicted by the group. Oxygen's got 6, so it wants 2. We're not going to worry about it wanting 1. Does that make sense? Okay. So guys, this then is the idea with oxidation numbers. Any questions? Because if not, what I'm going to do is I'm going to show you the steps for figuring out these chemical formulas. Then we're going to do 3, and then you are going to work on your homework. You guys good to go? Any questions on oxidation numbers? These are the charges. Where do you find the oxidation numbers? On your periodic tables. What do you do if there's more than one oxidation number? Look for the Roman numeral. You good? Okay, here we go. So guys, how then do we write chemical formulas? Well, scratch these down with me. Here are the general rules for writing ionic formulas. Writing the formulas for salts. But guys, I would propose to you that you already know all of these rules. I am not going to teach you anything new today. Here's why. Ready? Right there. That is why I know that you guys already know these rules. Because you guys all know what's inside here. Don't say salt. What's inside here? Sodium chloride, right? So this is a salt. This is the salt. Sodium, which is a metal. Chlorine, which is a nonmetal. This is sodium chloride. What is its chemical formula? NaCl. You guys all know that? Sodium. So y'all know this. Table salt is NaCl. You don't need to write the things down in blue, by the way. Guys, table salt is NaCl, and we call it sodium chloride, right? Yeah? Okay. Here's rule number 1. You need to write this down. When you write down chemical formulas, they are always written cation first. But guess what? You already knew that. How do I know that you already knew that? Because guys, you would never call table salt ClNa. Looks stupid, right? We know the table salt is NaCl, it's not ClNa. Why? Because it's always cation first, and sodium is the cation. ClNa just looks stupid because that's anion first. That's rule number 1. Rule number 2 is this. All salts have a neutral charge. You may remember I asked you a homework question about this last unit that says, why is it that table salt doesn't have a charge if it's made of ions? And what did we learn? They cancel each other out. There's the same number of positives as negatives. So when we say salts have a neutral charge, it means there's the same charge of positive and negative. How do I know you already knew that? Because you know that table salt is not NaCl2. That looks wrong. The reason that it looks wrong is sodium is +1 and chlorine is -1, and you only need one of each to cancel each other out. Okay? Rule number 3 is this. When you name salts, the name of the cation does not change. But guess what? You already knew that. How do I know that you already knew that? Because this looks stupid. Table salt is not called sodiumide chloride. That doesn't look right. The reason is because the cation sodium's name does not change. Yeah? So guys, what about this last rule? When we name salts, the anion's name, we drop the ending and add IDE. But guess what? You already knew that too. How do I know that you knew that? Because I know that none of you would ever call this stuff sodium chlorine. Sounds weird. And maybe you've never even picked up on this. But guys, chloride is not an element. Chlorine is the element, and when we put it in a salt, we drop the "ide" and add "ine." And so this is not sodium chlorine, this is sodium chloride. Get the ideas? Okay, so these are our guiding principles. But now we've got to figure out, how do we come up with the ratios? How do we know how many atoms of each we need in order to balance the charges? Well, guys, the answer is this. Write this down with me. You need to go back to 3rd grade math, and you need to remember about this concept called the least common multiple. The LCM. So you ready? Let's talk LCM, shall we? So guys, here are two numbers. What is the least common multiple? No, so be careful. 2 is the lowest common factor. That is not the same as the least common multiple. What is the least common multiple? 12. So let's remember. Guys, the multiples of 4 are 4, 8, 12, 16, and so on. Then guys, the multiples of 6 are 6, 12, 18, 24, and so on. So the least common multiple is the place where they first match up, which would be 12. Now guys, the question is this. Why do we care about the least common multiple? Well, here's what's going to happen. Imagine that we have a cation with a charge of +4. And imagine that we have an anion with a charge of -6. Where's the first place we can get the +4 and the -6 to match up? At 12. So if we have 3 +4s, that gives us a charge of +12. If we have 2 -6s, that gives us a charge of -12. And that's the first place the positives and negatives will balance. Okay? So, why do we care then about the least common multiple? Or lowest common multiple? Guys, we do that because this determines the charge at which the positives and negatives will first balance. All right, guys, you're almost done. Now all I got to do is give you the 5 steps for writing these formulas. We are going to do three of these together. And then you're going to work on your homework, which you'll get done. You guys all caught up? All right, here we go. So guys, steps for writing the formulas for salts. There's 5. Once you're done writing this down, you're done taking notes, we'll then look at 3 examples and then you're going to get to work. So guys, here we go. Step number 1. First thing that you've got to do is write down the abbreviations for the elements. Some of you initially are really going to struggle with this because 1, your handwriting is horrible, or 2, you're lazy. So guys, understand, I'm a left-handed guy. I have every strike against me, and I can write legibly. So can you. Guys, understand the first letter is capitalized. If there's a second letter, it's lowercase. If you're one of these people that puts flowers or hearts for the dots for eyes, knock it off. Guys, it's capital and then lowercase. Don't struggle with step 1. Step number 2, you determine the charge of the ions. Where do we get the charges for the ions? These are the oxidation numbers. We get them off the periodic table. The first one will be positive, the second one will be negative. Then guys, step number 3, figure out the least common multiple. Guys, at first, I will write this out for you. But quickly, I hope you don't need to do this. You're welcome to if you want. But guys, understand, this is one of these processes where very quickly we shouldn't need to see your work. You should be able to look at a formula, or you should be able to look at a name and write down a formula without doing any of the background stuff on paper. So as much of this as you can do in your head, the better. Then guys, step 4, you are going to determine how many of each ion you need. And then, guys, finally, step 5, you're going to write the formula given the subscripts that you figured out in step 4. So that's it. We're going to do 3. Then you're going to get your homework done. It's a beautiful thing. Are you ready? You good? Can I get rid of this? You all caught up? Anyone still need it? Okay. How about now? Okay, here we go. So guys, we're going to do 3 examples. You don't need to write this down. These are the instructions out of your homework. You're just going to write the chemical formulas. So the first one we're going to do is calcium chloride. Guys, again, I'm going to very methodically go through these steps. If you find yourself, but be careful. Don't give yourself this freedom until you've earned it. Do the first of these, the first 3 or 4, very methodically. Then if you find, oh, I could probably do parts of this in my head, do it. Because quickly you need to get to the point where you can just do these without writing any of this down. But guys, step number 1 is what? Write down the abbreviations. Calcium, and I'm going slow. Guys, calcium is element number 20, big C, little a. Then guys, chlorine, our trusted friend, element number 17, Cl. Big C, little l. All right, now guys, step 2, we need charges. Where do we get the charges? Those ridiculously small numbers on your periodic table. What's the charge of calcium? And you know what, I'm going to move these down a little bit. Calcium is +2. Then guys, we need the charge of chlorine. Oh no, there's like 11 of them. So right, guys, that's the trick. There are a pant load of charges for chlorine, but only one of them is negative. And because chlorine is the anion, the non-metal, we're going to use the negative charge. By the way, how do we know that chlorine is the non-metal without even looking at the periodic table? It's second. It is a halogen, but guys, it's second. The second one's always negative. So what is the only negative charge that chlorine can take on? -1. Okay, now guys, step 3. Guys, for step 3, we need to find the least common multiple. So I'm going to do this. You don't need to if you see it, but I'm gonna. What are the multiples? +2, +4, +6, ... -1, -2, -3, -4, ... Okay, now, where is the first, just a second, where is the first place that the positives and negatives meet up? 2. If you find it helpful to circle that, go for it. You know what? I'm going to try this. Let me see if this helps to circle this differently. I never tried this before. So guys, the first place these meet up is at 2. So here's the idea then. The positives and negatives will meet up at 2. Each calcium has a charge of +2. So how many do we need? 1. Then guys, each chlorine has a charge of -1. How many do we need to make a charge of -2? 2. So we need 1 calcium and 2 chlorines. So now step 5, this compound is Ca, 1Ca, and then Cl, 2 Cls. So calcium chloride is CaCl2. What questions do you have? Kat, do you have one? Yep, did you get it? And again, guys, quickly, if you're comfortable, you don't need to write out the multiples if you can just cook this in your brain. You guys good? Questions? 2 more. You're good? Let's try one more and then one that's tricky. Okay, guys, number 2, aluminum sulfide. I should have brought this. So, guys, all of these I have in bottles. Aluminum sulfide's really kind of pretty. It's this really cool, like, spidery almost. I will. It's cool. Anyway. Or at least it's cool in the form that I've got it. They then grind it up into powder. But anyway, here we go. So guys, aluminum is element number 13. We are going to start by writing down Al for aluminum. Then guys, sulfide is sulfur. Remember, drop the ending and add IDE. Sulfur, element number 16, is an S. Now again, we need to know the charges. You look at aluminum, element 13, that's plus 3. Then we look at sulfur. My guess is that depending on the periodic table you've got different answers for the charge. But guys, only one of them is negative. And what is that negative charge? -2. Does anybody have any other negative charges for sulfur? Good. Okay. Now guys, step 3, or I don't even know the step numbers. Next thing we need is the multiples. This goes plus 3, plus 6, plus 9, and so on. This goes -2, -4, -6, -8, and so on. So where is the first place the positives and negatives meet? At 6. So how many 3s make 6? 2. How many 2s make 6? 3. So that means if they meet up at plus 6 and minus 6, we need 2 of the aluminums and we need 3 of the sulfurs. So this would be Al2S3, and that would be the formula for aluminum sulfide. You guys doing good? All right. We got one more to go. The animation in this is subtle and yet impressive. You ready? Guys, the next one that we are going to do is iron nitride. Here we go. We're going to write this down. Iron is element number 26, and its abbreviation is Fe. Then, guys, nitride is nitrogen, and we look up nitrogen, element number 7, and it is N. Okay, so now guys, the next thing that we need is charges. So we look at iron, it's the positive one. What is the charge of iron? 2. +2, or 3, or 6. Which one are we going to use? The one that's in bold? No, we already covered that ground, right? Which one are we going to use? We don't know. We're done. You can't do this. You cannot do iron nitride because iron has got more than one charge. So how did we say we were going to fix this? And watch the animation. You ready? You need a Roman numeral. You can't do iron nitride. You need a Roman numeral like a 2. Now guys, be careful. That doesn't mean use the second charge. It means use 2. So guys, the charge for this is +2. Now understand, I could have just as easily done +3, or I could have done +6. And guys, here's the thing. I have all 3 of those in bottles. I have iron 2 nitride, iron 3 nitride, and iron 6 nitride. They all exist. I have them all in bottles, and they're all different. They have different chemical and physical properties because they're not the same salts. I just chose the 2. Now guys, we need nitride. If you look at nitrogen, it's got a pant load of charges. Which one do we use? The only one that's negative, which is what? -3. So now guys, let's do this. Yours also has -2? Good. Now let's talk. So guys, and mine doesn't. Mine only has as a negative charge -2. So guys, or I'm sorry, -3. So what are we going to do? And remember what we're going to do. If yours if yours has more than one negative charge, guys, here's what we're going to do. We're going to go by the group. So nitrogen has got, hang on, pay attention. Pay attention. Savannah, you don't want to miss this. Nitrogen's got 1, 2, 3, 4, 5. Nitrogen's got 5 electrons, so how many does it want to have? 8? 3? That's what we're going to use. Get it? That's going to be our tiebreaker. So now, guys, let's try this. Forgive me if this is too fast, but let's try it. Let's see if we can figure out the formula without writing down the multiples. What is the least common multiple of 2 and 3? 6. Now, guys, go like this. How many 2's make 6? 3. So that would be Fe3. How many 3's make 6? 2. So that would be N2. So, guys, this is iron 2 nitride. But some of you right now, and guys, watch close because you're going to make this mistake on the test and there may not be remediation. Some of you right now are going, no, it's not. This is not iron 2 nitride because there's 3 irons. Do you see the mistake in that reasoning? The 2 does not tell you how many. What does it tell you? The charge. So guys, iron 2 nitride has 3 irons because that's how many is necessary to balance the charge with the nitrogen. Do you get the idea? Okay, so guys, we are done. Grab the homework packet, let's answer questions, and then we'll talk about homework. Yes?
If it was like, I guess, is it possible for that kind of second part to have a negative number on the bottom there?
No, so this is how many of them there are, and you can't have negative numbers of things.
Oh, okay.
Yeah, it's how many there are. Okay, guys, so take a look at the homework assignment. You'll notice that there are 15 of these for you to do. I think that it would be valid to just do them on this piece of paper. These aren't terribly space consuming. Guys, if you can do what I did on the board just a moment ago, and if you can do these without writing down the multiples, that's completely legitimate. And then, guys, you'll notice that there are 3 free response questions at the bottom. Address those as well, and we will grade these on Friday. Go get them.